some viewpoint might be very radical, but feel free to ask them about your question. Yeah. Still, I think this is common for all the culture. Right? knows him, and his talk today is not very theory. It's about the topic is Qingyu. I am speaking. Hello, good morning. And Richard's topic will be Did AI solve programming contest? Let's welcome Richard.
Test? Okay. Now it's working. Awesome. Okay. Thank you everyone for waking up early for this. Thank you to the organizers for running this great event and for having me, for letting me give this talk. I will be talking about some recent developments in these advances in AI for problems solving. And first, let me start off with a little bit of a background about myself. This is kind of like a hidden, well, probably not as well known aspect of what I do. Is actually before I was a theory researcher, I actually got into doing theory through problem setting, basically. So I had a summer job where I went to Egypt and I wrote some test data for IOI. And the next couple of years, I was a problem setter and problem author. One thing led to another. I got elected to the IOI problem setting committee. And then I was also more recently kind of did some training and also was a problem setter for APIO. I'm sure you all have seen this, right? How many people here have not seen this? So the last year, there was some claims that by both Gemini and OpenAI that LLMs got some really high ranks on both the IMO and the IOI. So since we all know this, let's first see some reactions. Yeah, my favorite is from Gennady. Where's Gennady in the room? Or it doesn't matter, I guess, but oh. Says Cognition is the first AI lab to win a verifiable gold medal at the IOI. Our human, Ryan B. AI, placed 7th overall, impressively competed under exact same circumstances as all the human contestants. This post was made before we actually know what the score AI got. And so the slight issue is that when then the AI score came out, right, OpenAI said we got 6th. Which then still leads to the question of like, where is this all going? This question, I mean, there's some thoughts, maybe AI can't really do combinatorics. I mean, this has all been tried in the past year, like AI maybe can't do constructives. AI didn't solve the grid problem. There was a theory maybe AI can't do grid problems. And then the past year, right, 5.2 came out, ChatGPT 5.2, and then 5.4, and then a couple of weeks ago, 5.5. In fact, actually, this slide deck got rewritten when 5.5 came out. The current kind of thing is that for those, I put question marks because for all of them, we actually have examples now of AI solving them. And it also doesn't help that you have friends from contest days who have access to like backend cloud. The backend cloud stuff is really scary, just for the record. So the current thing that seems most reliable, what I hear, is AI can't handle long logic chains. But how long will that last? I mean, this is causing, I'm not sure how many of you like follow the research community, but research community have a lot of concern about this. The most radical thing I've heard is in 5 years, like, no, I actually have a bet with a friend about like in 5 years, humans can still prove a theorem. Like, it's not just cheaper to just like, just like prompt the AI and have the AI output the answer. So for this talk, what I'm going to do is I'm going to give my perspective on the progress made in AI problem solving. I will start with a situation from this year's Chinese winter camp, which was announced quite a bit in China, but probably is not very well discussed more globally. And I will discuss what I feel are the strong points of AI for programming contests. And then I'll leave with some questions, both for the AIs and for the humans. So this is a case which I'm not sure how many are aware of this, but at winter camp this year in China, so winter camp is the pre-TST round. Actually, I think now it's like most of the students just take the round that is basically winter camp. The general students take the first contest, and the people doing the TST take both contests. This is like basically China IOI TST. Yeah, and this year what they did is that they let the top. They gave 30 students access to the latest LLM models available in China. So this is things like QWEN and also DeepThink. And then afterwards, there was this report that they kind of posted on WeChat, but actually the report itself, I'm not sure, I think the report never actually was posted. But here's the rough translation from what I got. It says that basically at the time of the winter camp, when they test these models, that it's out of 300, like any IOI problem set is out of 300, right? So the max score is 194, the average is 100, and the most important part is that the scores of the contestants were roughly proportional. So if you like take the contestants' previous scores and you look at what they got with the aid of AI, it ended up being roughly proportional. So this is one of the best part about LLMs now is I can just give you the exact same thing on the left, but in English here. Okay, so far so good, right? But of course, there's a couple of very natural questions that to be asked. One is, what happens if you use the other models? The second question is, are these problems truly LLM-proof? And so 5.5 came out, and then we immediately tested it. So this is actually Gemini 3.1. This is with the help of somebody who can do Gemini 3.1, and you see that on problem 2. So the problem 3 somehow is still not able to get, it still gets a 0. But on problem 2, which was at the time of winter camp, basically they were claiming this was immune. Actually, I actually had some doubts whether it was immune because I felt it was just on the boundary of what's doable and what's not doable. It gets 100 now. Of course, so this means that as a scientist, right, you start looking to more like what is the difference between 5.2 and 5.5 or like 3.1 and 2.8 Gemini that's leading to this. And then what you do, right, you look at what the LLM is outputting. So the good thing with the LLMs, you can actually take their trace. You can take their solution. Like the LLMs are actually very good at like explaining things because Like, it's actually very good at turning math into like reliable text. So one thing we did is we got the LLMs, we asked, hey, how did you solve the problem? We took their thinking process, and we had them output all their steps. So on the left is GPT, on the right is Gemini. I'm sorry that I do not have time to go through the problem statement. We're all problem solvers. I'm sure you all would like to know what the problem is. Unfortunately, I only have 30 minutes. But I do want to bring your attention to a few things. The thing that's very curious about these is that both solutions have the exact same algebraic transform. Then they make the exact same conclusion about what you're allowed to do. I mean, the problem is about a mouse named Jerry and a cat named Tom. So if you see cat, it's just like something in the problem. You see that both solutions actually say roughly exact same steps. At least their start. So the solutions start off by doing exactly the same things. And at that point, I mean, this is from somebody who has dealt with students who turn exactly the same homeworks, right? The first thing you do at that point is you go ask, hey, like, what does winter camp solution slides look like? Any questions? So then we pull up winter camp solution slide. And what it says is first rotate everything 45 degrees. It's a vertical upward and horizontal path. And then basically I try to look for something that basically you get the solution slide has a succinct description that ends up being exactly what GPT and Gemini outputs as their explanation. It gets even better. The code outputted actually are different. The code outputted are different in that I think Gemini is the one that threw a KD tree, timed out a bunch, and then eventually made it fast enough. GPT just went with like a sec tree and then also wrote it up. And also makes you wonder why they did start doing different things. And you look at the solution slide. This is where the solution slide. Solution slide says basically, hey, like, here's how you do n cubed k, but hey, like, you're in China, right? You should know how to speed this up. So it just says like, hey, like, just do any kind of seg trees. It's going to do the same thing. So the other indicator that I claim that the LLMs are strongly using the solutions themselves is that once the solution becomes vague, they do different things. I think there are some very curious takeaways from this. At a technical level, what it means is that the LLMs must have some kind of solution database. They have very strong ability to take text and turning them into correct C++ code, at least from the sense of programming context. They have a very good text-to-code ability at this point. Of course, the other thing is that they all call the min-cost flow, so they also have library checker. Like, they're not making min-cost flow with like dual potentials up on the spot. This also says something at a very high level, I feel. I say that it feels like at this point that the LLMs are, instead of general purpose tools, like you hear a lot, you hear about AGI, right? Like these things are basically intelligent systems. The fact that they can take a winter camp solution slide to produce you roughly that code, in my opinion, means there's a huge amount of resource devoted to just improving LLM performance on programming contests. For us problem setters, I claim this also caused some issues, right? It says that basically the way we can test LLMs is pretty much as soon as a problem, before we post solution slides, we can. That's like the only window in which we can really reliably test the LLM. And then the last item is because if you think about how much trouble LLMs went through to solve these problems, like this problem, when I looked at it, I did not think this is LLM proof. I actually thought like anything where you reduce to min-cost flow, there should be a fairly direct, like it's a seg tree and a min-cost flow at the end of the day. You just chug some formulas, it's gonna solve it. Like I did not think this was an LLM proof problem. So the third point is actually that competitive programming has a huge amount of value. If you think about how much resource has been thrown at just getting better at CP, and you look at this problem, I mean, I urge everyone interested to look at this problem afterwards. That like you can still very naturally write problems that cause a huge amount of difficulty to LLMs to the point where they had to dig up the official solution, even though you tell it, hey, don't search anything. Any questions at this point? How am I doing for time? Okay, cool. So I want to then go into the details about a little bit more of what I feel are some things that, like, what exactly is this capability, right? Like, it's clearly not like a general intelligence system, right? They're getting to the point where they are, like, for problem 2 on winter camp, with the solution they can do it. For problem 3, they get 0. So there's a question also like, what are these things good at? What are these things bad at? And for this, I'll turn it over to you all. I think we should think a little bit, instead of thinking of them as intelligence, I mean, we like to really kind of, we like to call our AI names, right, at this point. But I would like to pretend it's still a machine. And I would turn over to the audience, and I would ask you all the question of, what are things, like what are your top 3 tasks where a machine is much better than a human at? Like, what is something that I would never try to, like, beat my computer at? Maybe talk with your neighbor, talk some ideas. Maybe we can vote for what the top 3 are. I guess there's not a board. Is there like something I can write on here? But I can just type into this laptop, I guess. But maybe just converse a little bit, try to figure out what are some things where, like, machines are much better than humans at. Give you all like 2 minutes. I got 4. The 4th one is really surprising. The 4th one is very good.
Obviously, it's like information search. Yeah. And then the interpretation, you have the notes of complete solution and translate it to the. Yeah. What about some of the things that debug? Usually it's good at debug. So I do, like, some student ask me, like, why I did a runtime error? I would just give the code and give it to the AI, and it told me that, okay, this is another possibility, and it works. So I think this is like, they are beyond on implementation, more like understanding the people, the code that people are writing. So I think it's really provided.
Oh, there. 是要想做一些修改，换成上写2个字。
就只能在上面，因为你连的只是有限的。这是开打的电脑是吗？
没事没事。
可以了吗？
可以了。
有鼠标吗？
没事没事。Okay, I have the slides working. Let's give it 30 more seconds, and I'll start collecting answers. Okay. Okay, what do you think? What do we think is the highest ranked one? What are some ideas? What do we think the highest ranked one is? Stupid computations. I'm going to write computations because I cannot write very effectively. Compute, right. Okay, hold on. Let me. Oh gosh. Okay. So the idea is compute. So basically, okay, what else? Information collection or search. Okay, cool. I'm good. Thank you. Anything else? Translation. So translation, I would put it as part of search. Okay, so translate is also there, okay? What other ones? That I would also this as part of search, right? Because how do you search, right? You download all the internet onto a disk, and then you. Sorry. Huh? Sorry. Writing a lot of code. Okay, so doing a lot of things. Yeah, so just. Content. Right. So so I think it's actually kind of funny. We came up with exactly the same items, I feel. Yeah. So. Yeah. So okay. Any other things that people have? Any other thing that come to mind? Okay. Sorry. Memory. So memory, I would put as search, right? Because how do you do translation, right? The way the machines do translation is they just have like a lot of text snippets, and it's basically like a lookup engine in that sense. Yes, Stan. Sorry. Planning. Oh, you guys are good. Planning. Okay. Scale, right. Yeah, content generation, right? This is okay. So you say you would put that as scale. Yeah, scale. Content generation. Okay, let me take a photo of this because I will release a version of this. Anything else? Yes, yes, completely agree. Hold on, let me just take a photo of this so that I can go edit my slides afterwards. Anything else? Do what? Oh no, I meant problem solving, right? Like what is something that, I would put that also as content generation in some sense, right? That in some sense is content generation. Yeah. Okay, yeah, I guess in the interest of time, let me move on. I'll show you the top 3 that I came up with before the talk. My thoughts were it's good at computation, searching and info retrieval, which I think we also added translation in there. And I didn't think of the word scale. I actually really like what you said about scaling, but I was just gonna say it's really good at trying lots of things, which I guess is also what you were saying about, right? Let me give you examples of each of these now. Let me give you a problem that obviously we can never beat an LLM at. Problem is, here's a 10 by 10 symbolic matrix, compute means determinant mod x to the 97 plus 1. I'm not even sure if x to the 97 plus 1 is reducible. This is something I don't think we ever want to try to, unless we have the right computational algebra packages, right? You'd never want to beat a machine on this on a piece of paper. Like scrap paper on a U versus a machine, you're just duped. I claim that we ask this kind of problems. There's a lot of problems right now that we input an algebraic structure and we output the result of some manipulations using the equality sign. Examples of this on the IOI are things like Bellman equations, Beech tree. Last year, I would claim the first problem last year on the IOI souvenirs was actually upper triangular matrix. And then last year's P2 was a reduction using symmetric algebra to triangle counting. We actually have a lot of problems right now where we're just doing some symmetric algebra to the point where we get to a problem that is also in database. Any objections to this claim? I know I'm making some very, very like controversial claims, but I claim that a lot of these very hard problems, especially for humans, fundamentally they are like fitting some equations to a fairly like equation-based setup. And a lot of them, I claim that with a sufficiently good algebra engine, you can just like pull it out of the algebra engine. I also want to say in a related work, yeah, Jaehoon?
I can see the logic, but also it would be appreciated if you can back up with the actual like model warning, because from what I remember, I think the AI actually did not hold supervision. So if this is
Oh, no, no, no. AI, no, AI is a score. Wait, AI didn't solve souvenirs?
I think so. So if this is like backed by evidence, I would really appreciate it. Although I know the like logical chain that kind of results in this idea.
Yeah, okay, so the question is we should go check the AI score on this. Maybe let's do that offline. How about that? Yeah. Okay. I also want to add that the same situation is happening on the math side. Like IMO short, I'm not sure how many know the IMO shortlist. Like on the math side, basically number theory and like polynomial-based algebra and most inequalities are just solved by LLMs for very similar reasons. Okay, next item, search retrieval. I would not want to, like in the LLM age, try to like beat the LLM on this problem because the LLM has PQ trees. So this is actually a 1976 paper from Interval Graph Recognition, where they just worked out all the cases of like how this is actually a tree. And like the solution IPSC, even the internet on the internet problem solving contest itself, the solution is just here's the paper to PQ trees, read it. In general, there is a trend also that's basically that we ask a problem that's well studied in some circles. And then the output is a solution from the textbook or the paper. Paper as in bracket CTSC paper as well. Yeah, I'm not sure how many of you know about the CTSC. How many actually know about the CTSC papers? The rough amount of papers generated over the last 25 years is about, I think they generate 200 pages a year, 25 years. You can figure out how many pages has been generated. Yeah, no, there are some actually there are some examples of this. Actually, the first one I'm actually very guilty of. This is the aliens from IOI 16. And I think at that point, I was hoping to like have a discussion afterwards, but people liked this problem so much that they wrote so many problems based on it that somehow this got lost. But I mean, for those who, I mean, there were several people in the room who were in the room when we like converged on this, right? And I think it's fair to just say at that point that the only reason this problem was actually submitted to IOI 15, it was actually the author themselves actually didn't know this trick, but like people on the committee knew this trick. And this problem was actually the only reason it got put on there is because there was like a whole bunch of other like zero-day things that like other teams knew. And then like somehow like we had to balance between like things that like, we had to basically end up balancing between a bunch of literature search problems. So, but then we kept on giving them, right? So then there's like IOI 19, once you know ST ordering, you solve it. Books was an ESA paper. Skywalking was a Watts paper. Keys is like an exercise based on Targent's algorithm, and then Mosaic was just straight up AG, was an ad-coded regular, I believe. Yeah, no, that's basically a problem search engine, right? Like a problem search engine can just go do these problems, and then on recent IOIs, right, like the 22 and 25, we gave a lot of range Cartesian trees. Range Cartesian tree, the citation is YNOI 16, but then also appeared on IOI 18. So it's also like like even among IOI problems themselves, the very hard problems, there's a lot of repetition. And this is something that like a problem search engine is very good at. Let me get to the third kind of things that you never want to play against the LLM at, which is just winning the lottery. Right, so there is the kind of problem which is like, like I give you a one-way function, generate me a x where the one-way function has a certain number of zeros. If you're good at this kind of problem, much better than a machine, you can go make a lot of money. Like this is basically how modern blockchains kind of hinge upon. But in general, basically the kind of the style, I call it vibe ACing. Yeah, what's vibe ACing? It's like it's an unmotivated abstract thing, and then you'll do something that feels right, and it works. Yeah, like the story I heard is like the people who got Beech Tree in 23, they came out and go, this is the most scary thing ever, because like I have no idea why my solution worked, it just worked. So like this actually goes back way before like the modern like scoreboard of threes on the IOI. Like this goes way back. Like pebbling odometer was the first time I've seen this, which was pebbling odometer was this like hard problem in 2012 in Italy, where it's possible to go for a log 30, well, order log 30 solution, or you just do 30. Turned out that 30 was better than log 30. And like there was no way to know. And you do one of them, you lose points. So like this is like one of the things that have happened. And then more recently, we have a whole bunch of these. Like, I mean, I will get to festival in a second, but I feel that one of the worst example of this was the one where GPT gets 58 and no human gets 58. Like there actually has been a case where like GPT got all the partials, but like humans couldn't even figure out what the partials mean. And like if you look at the GPT solution, it's like 200 lines of like just like if statements. Well, not like for loops and if statements, but like one for each subtask kind of thing. So it was longer than the actual official solution that gets 100. Okay, so that's a quick rundown of some examples that I think LLMs are much better than humans at. So far, I haven't any comments, questions about these. I'm about to then move to some high-level discussions. The first thing I want to point out is that contestants themselves know this. So, you know, Gennady made a post about RyanB AI, right? And here's RyanB AI speaking. This is actually before the GPT results were released. I actually asked him on Twitter, it's like, how do you think AI did? And his first comment was like, yeah, I was in a contest where I probably lost to an AI. So I didn't know why he said that. I was like, hey, Ryan, have a little bit more faith in yourself, right? Like you did pretty well on this contest. You solved like 2 problems each day, and like you're ranked pretty high. It's a pretty hard contest looking at the scoreboard. There's no way like. So it turns out the reason. So actually, I didn't ask him about how he got to this conclusion until about a month ago. So this is actually Ryan himself speaking. And then when he said that, basically it's like, I remember talking to like one of the guys on the Chinese team and just says like, you know, like, I kind of just guessed the number of DP states is small. This is on festival. This is the task on day 2 that 14 people solved. And the only observation he really missed was just, hey, it has 20, like a DP table of 20 times n works. It's not really n squared states. And then he also said that for P2, I didn't even prove it was n to the 1.5. He didn't even prove triangle counting worked. I just do greedy, and then, you know, like it just passed. Like it's a proof by AC, basically. So the things like the contestants themselves, right, when they talk among themselves, they kind of guess what they were missing, and they go, oh, these are actually things where the machines are very good at. So yeah, and my response to him is, yeah, this is just a standard checklist that, like, you know, like people who have coaches, people who are trained, they will run through this checklist. So which then gets to the fourth point. Who raised that to me? Oh, it was Stanley, right? Like they're very good at strategies. Planning, yeah. So actually, I think there's one that is also extremely overlooked, which is that when a coach tells a student go for this strategy, the students often will do something different. For LLMs are really good at execution. If you tell LLM, like, if you see this problem, try these 10 things. It's just a for loop, right? It will just do those 10 things. If it doesn't work, it will do something else. But it's very good at executing a bunch of pre-planned problem-solving strategies. And very often we get these things like, hey, maybe check if the DP table is small. Like, especially these days, because LLMs also have the ability to like generate a lot of small examples and look for some patterns. So it's actually very good like developing the problem space like automatically and like generating some of these things. I think the other point that needs to be mentioned is that there exists some very simple contest strategies that apparently are only known to people who do LLMs. Like, how many people in this room know that odd-year IOIs are a subset of are within the convex hull of the previous 5 to 7 NOIs? Like, how many people are aware? No, these slides will be made public. Like, I think by this point, the fact that LLM knows this means that we all need to know this. This is a pattern that held the last 20 years, for the record. Yeah, the things actually on the, so I used to coach for USACO. On the USACO side, we have known this since 2012. And like people like Yuzhou and Li Jie also knew this. Like when I talked with them when they were in Boston, they knew this since like 2013, 2014. I should also mention that we all know what happened in 2021, and that was actually the first year this was like announced to like a certain IOI team that this is a thing. And this was only announced once more to that team. And you can go look at the IOI scoreboards and you can see what happened those 2 years. Like, no, this is literally like, I mean, if you want proof, this is actually the proof from my slide deck from the Winter Camp 21, where we just like straight up say these things, like odd IOI year you do this, even IOI year you do this. And like we even said, hey, there's a 4 to 5 year delay. Like don't look at last year's CNOI and like use that as indicator for what to do. Yeah, by the way, it turns out this is really not well known. So if you have like comments about this phenomenon, you're going to discuss this phenomenon with me. But we should do that offline because this is a huge discussion. So I know Gu Yuzhou figured it out, and then Gu Yuzhou told Chen Lijie. That's like the way that I know about this. Yeah, so this is why I put WJMZ BMR. Like somewhere between Gu Yuzhou and Chen Lijie, they figured this out about that time. Yeah, and then the funny thing is like people like Scott, like they all know about this. Yeah, but the thing is like, I mean, when this happens to humans, they don't say humans solved IOI, right? So then finally there's the questions. Where are we? What do we do from this? So first I want to say that I also, because I want to put back on my hat as a researcher, I don't want to kind of talk completely as a contest problem setter. I want to first point out there do exist things that are very natural that LLMs are very bad at. So on the top right, once again, Ryan, basically we have this problem that called dynamic interval graphs that anytime a new LLM come out, we test for it. And then this is Ryan's comment. This is the third time Ryan has said this. Like I query Ryan this every 6 months. And then he says like it's trademarked, it's still 6 months away. The general way this works is that the things that seem to really, really break LLMs are things where it's a very natural setup. You need long logic chains, ideally at least 2 pieces interacting, preferably 3. They interact with each other ideally in a nonlinear fashion. Ideally, there's some recursion in there as well. The problem with doing things this way is that these are the most disliked problems. Like in this community and also as well as research, both communities, these are the most disliked problems. So like examples of this is like, like the dynamic interval graphs, also like, if you want another set of examples, and this is API 022. So my opinion, as I'm coming toward the end of the talk, is that whether AI has solved into programming contests is can we still make good contests that negate machine advantage in things like computation, info retrieval, scaling, and then just straight up execution of strategies. And I will finish by leaving the scores for the humans, which is essentially the question of what do we dial the difficulty or the score of the LLMs to, right? So it's like, what score should AI get on the IOI? My take is currently that for the ICPC and CF format, this is already very difficult, but I think there's a very real question, which is what score should we let LLM get on a contest? There's also kind of, because part of this is also speaking as someone who works with a lot of people who have done IOI, there's a question of like, if we get to the point where only AIs are capable of getting 600s, why do we even do this versus just like doing AI contests, doing research, or just straight up go work at an AI company? At a more technical level, I believe some good questions are how to test contests using LLMs. How should we allow AI to compete? Like there's some saying about maybe AI should have a power limit, should have a storage limit. And then also the final question is on the flip side is how should we let humans compete? Should we just give human LLMs and then redesign things that way? Thank you all for listening, and I'll stop here. Do we have time for questions?
Okay, thank you, Richard. And any other question you want to ask? Yeah.
What does the dial represent?
Can we talk about that offline? It's one of the most mysterious engineering contraptions. It's one of the more mysterious engineering contraptions in my mind. But I was actually going to ask, do people know what this dial is? But maybe let's.
Wait, shortest paths on dynamic interval graphs. You have to bet on one thing. First, one thing, A, there is a polylog solution for that problem. B, there is a polytime hardness for that problem. One of them is true. What do you bet?
Wait, for interval graph?
Yeah, interval.
There's a polylog.
There is a polylog. Okay, sounds good.
This is why we use it as a
By the way, I am still no fun. I'm still not 100% convinced that result. So it's Richard's independent thought, not mine. Okay, any other question? And so I want to ask this question to our chief judge, so Qingyu. So assuming a 13 problems contest, I'm not saying you can find out, this is independent. How many problems do you think that you should allow AI to solve if you are able to make it happen?
Well, it will depend on stress or AI. I mean, if you ask me this microphone. I mean, well, I mean, if you asked me this question 1 year ago, then I would probably say 0. But I want to know if how many problems should be in the future, because I think some of you have heard that in the last UCAP stage, when the best team only solved 9, the LLM is able to solve everything. So, yeah, who knows?
Okay, so I think that if do you have any other question? If no, then we can move to our next speaker. Okay, thank you, Richard, again. Wonderful speech. Okay. Okay, so our next talk will be by Professor Zachary Friscott. He's an associate professor at the University of Alberta. His research interests primarily concern combinatorial optimization, with emphasis on the design of approximation algorithms for NP-hard combinatorial optimization problems. So this includes, but not limited to, problems in data clustering, vehicle routing, and network design. And he also earned a bronze medal with the Alberta team at 2006 ICPC World Final and continued to involve through coaching and problem setting for ICPC regional contests. His talk will be about problem solving beyond competitive programming, research in algorithms. Let's welcome.
Test. Thanks, Jingbang. And first, I want to say thanks to Huawei for organizing and supporting this event. This is a beautiful place to hold it. And I want to say thanks to UCUP and all the organizers, too. It was a really exciting contest. Okay. Let me start with an about me. Let me just figure this clicker out. Okay. I'm a computing science professor at the University of Alberta, as Jingbang said. And I guess if you don't know where it is, it's right there. About an hour-and-a-half flight from Vancouver. I competed twice in the World Finals, and I had to put this up here because we got a bronze medal. I was happy about that, but I think we were happier about beating Waterloo that year. And while I'm a faculty member, I'm still active in the community. I'm a longtime coach of the U of A team. I frequently problem set, judge, and occasionally host the official ICPC regional contest. I know the concept of a regional isn't universal, but it's what we do in North America. I don't have as much experience as most people in this room. I didn't get started with competitive programming until halfway through my undergrad studies. I didn't have a clue about it until then. Trying to figure out the next step, and I want to talk a little bit about what research looks like from my perspective as a CPer. Some of you are already well settled in your careers. I still hope you enjoy this, this talk somewhat. So I study approximation algorithms. These are traditional problems. They could read like a contest problem, input, output, usually a discrete solution, except they're hard. They're provably hard. And if you take an algorithms class, you'll, maybe in your third year or second year, depends on where you're studying, you might see some proofs as to why some of these things are hard. And then depending on what the algorithms coverage is at your school, that might be it. It's hard, let's move on and study easy problems. But I like to study them still, the hard ones. So I'm going to give you a very simple example if you've never seen one before. TSP, the traveling salesperson problem, the classic one. Visit all the locations, come home, do it as quickly as possible. So a simple polynomial time algorithm that doesn't perfectly solve it, but it still is, I mean, there's some bound on how poorly it performs, is to compute a minimum spanning tree of the locations. Since the optimum solution connects everything in a big cycle, the minimum spanning tree is no more expensive. But now we can just do a depth-first traversal of the minimum spanning tree, and if you like, you can bypass locations you've already seen by just taking a shortest path. But the cost of your solution is no worse than twice the cost of the tree. So that's the 2 approximation. This is like Approx 101 right here. This is the sort of problem solving I'm talking about. There's many other angles you could approach one of these hard problems with. Maybe you just want to come up with like a better heuristics that solve them more quickly, even though it's still exponential time. Or I like to design algorithms with proven guarantees, even though it's a hard problem. So one thing is that many of the problems that I get to look at don't really show up in CP. They're just hard. Clustering problems don't appear very often. There are some exceptions, clustering on the line, and a few other interesting cases, but by and large, they're very rare problems in CP. The idea is generally you've got some points, arrange them in clusters, minimize some objective. By far, the most used clustering model in practice is k-means clustering. Where you want to minimize the sum of the squares of the distances, there we go, of the points to the nearest centers. So maybe there's some points here. We pick 3 centers if k equals 3. In learning, we think there's k different sources, and we want to classify them according to their source. And sure, you can come up with a one-dimensional version of this that you can expect polytime solutions for, but even in the plane, it's NP-hard. So results in my field would look like the following. In fact, very recently, just a couple of months ago, an improved approximation was presented for k-means. 5 plus epsilon for any constant epsilon greater than 0. The running time degrades as epsilon shrinks, but it still remains polynomial for any constant. But if you're talking about the Euclidean plane, you can get much better approximations, near optimal. Again, the running time degrading as epsilon shrinks. Another example, well, there's some vehicle routing problems we see in CP. Classic TSP, I'm sure everyone in this room knows the dynamic programming approach to TSP. But you can easily ask variants that are important. What if your vehicle can only visit a few clients at a time before it has to return for a resupply? Like it can only deliver C packages for some value C, or maybe non-uniform package size. Like it can only load up a bounded size of packages and deliver them to clients. So I've stated some approximation guarantees there. I mean, it's not important that you memorize what those are. It's just important that you see that this is an active field. And some of the ratios get a little funny. I was actually thinking about this when wandering around. Sometimes there's scooters just nicely arranged for people to ride, and sometimes they're gone. And sometimes you see a vehicle, like this little flatbed vehicle, carrying 3, 4, 5 scooters at a time. And I don't know exactly what they're doing, but I suspect they're rebalancing and rearranging, getting ready for the next round of demands. So this is a more general version of it, where there's not just central depot, but this is a nice optimization problem. Given scooters and locations where they should be, any scooter can go to any location, but we want to make sure that the sources are relatively balanced. What's the cheapest way, the quickest way to deliver the scooters to the start locations? So far, there's only a 5 in theory. That's really bad, but it's a nice problem to work on. And one more example before I get into the main point of the talk. Again, just showing you that there's all these interesting problems that don't often appear CP. You've probably seen Steiner tree in some CP problems. But just quickly, if you haven't, you've got a subset of nodes in a graph, and I only care about connecting them. So not a whole spanning tree, just make sure this subset is connected. Other nodes that aren't important, I don't care if they're in there. They may or may not be. This is NP-hard. There's this nice 3 to the k algorithm you might be aware of, where k is the number of terminals. But what if it's a big instance? Well, that doesn't work. So again, there's approximations and there's generalizations. What if you want to buy the cheapest way to connect them so it's a robust network? And questions like this. Okay, well, that's an example of some questions you can see beyond CP and that people have results on them. But this is the part of the talk I was not quite sure if I want to do it this way, but I think I want to go into detail with one of these. I want to talk about Euclidean TSP. The reason I want to do this is when I learned about this, as I was reading the solution, it felt like I was solving a contest problem with a little bit of extra stuff for approx. And then I've used that as inspiration in some of my own research. So let's step through this one. Now, if you've never been to a research talk before, I'm not going as deep as a proper research talk, but still there might be parts where maybe you kind of forget what the thread is that I'm pulling. That's not the point of this talk. I want to show you some ideas, but I'm not expecting you to reconstruct it on the fly. Maybe it's like reading an editorial where you just read it to see roughly what happens, but you're not too worried about the details yet. Okay, so classic TSP, except we're in the Euclidean plane. And this is actually a pretty practical problem too. Printed circuit boards with holes, sometimes they have hundreds of holes. Usually they're under a stationary drill head and the platform underneath moves. And that's exactly Euclidean TSP. It's not just about salespeople. Okay, so let's talk about this approximation by Sanjeev Arora. He gives a 1 plus epsilon approximation for any constant epsilon. We'll see roughly how that comes into play in the algorithm, but I want to talk about the problem. So Arora starts by overlaying a quad tree. So a big square divided into 4 squares, those divided recursively into 4 squares, and so on, up until each square is a singleton. And through some minor pre-processing, you can assume that the depth of this quad tree is log n. Now, we don't actually know what the optimum tour is, but it's good to imagine what it could look like, because we're going to talk about what we need to actually do in our algorithm. So there's a quad tree, and let's envision the optimal solution. The second thing that Arora does is he installs portals around the boundary of every square in the quad tree. So portals around the big square, portals around the inner squares, and so on and so forth. The number of portals around the boundary of any square is logarithmic. Don't worry too much where that comes from, but it comes from the fact the depth of the quad tree was logarithmic. And then he says, what if we consider optimal solutions that have to pass through the portals when they go from one square to the next? And he shows that there exists a placement of the quad tree, so maybe some sliding of it, some translation of it, for which the optimal solution doesn't increase by very much. So now we're going to try to find the optimal TSP solution, but it has to pass through portals when going from one square to the next. Now we're phrasing this very much like a CP problem, although I mean the log in around the boundary, that's a funny parameter, but in general it's a very rigid problem now. And we can solve this in polynomial time. It'll be exponential in the number of portals per square, but that is polynomial. So again, I'm going through this just to show you, I mean, just how hard DP problems can appear in research as well. So let's make a couple observations about the best portal respecting tour. So those little dashed lines there, that's supposed to be parts of the optimal solution as it passes through this cell. You can prove that it uses each portal at most twice. So if the optimal solution entered via portal and then somehow maybe entered by it again, there's some like untwisting operation you can do to get a cheaper solution. So the optimal solution uses each portal at most twice. And of course, the optimal solution will never cross itself. That's kind of standard for any Euclidean TSP. So with these observations, I claim we can finish a polynomial time algorithm to find the optimal portal respecting TSP solution. By the way, how many people have seen this in detail? Yeah, not many, a few, okay. So the DP table is pretty simple to state in English. The table is F, it's indexed by a square of the quad tree, and by P bar. P bar is just describing how the portals are paired up. So P bar would describe that, well, this portal will be paired with this one, this portal will be paired with this one, and it will also be paired here, this portal. P bar will describe the pairing. I claim the number of pairings is polynomial. Does anybody see why the number of pairings should be polynomial in this case? A better way to think about it is singly exponential in the number of portals. Well, the tour might enter through a portal and then exit back through the portal again, like if there's just something just barely beyond it. But it'll only, if I pick an arbitrary orientation of the tour, it only crosses once this way and then once back, at most. Does anybody know like this? Well, it's kind of like we're bracketing things. We're adding parentheses to things. Like it's, if I were to like take this part here and like cut it there and look at like the intervals across the interval that you would get by cutting there, they would be nested. And that's related to Catalan numbers. So you can show with just a bit of math that basically the number of portal pairs that you have to worry about is limited by the Catalan number on like O of the number of portals. the 2 there is because you can use each portal twice. But the thing about Catalan numbers, is they're singly exponential. So this is truly polynomial, in theory at least. And that's it. So that's the DP table size. The recurrence itself is, I mean, now that if you know the DP table, you can probably just work this out. If you're not worried about practical running time, you just want, in theory, it's polynomial. So what you could do is you could just say, well, I'm going to try all ways to describe portal crossings for the children of this square in the quad tree, and they have to be consistent. So they have to agree with our portal P bar for the outer problem. They have to match up at the inner portals. When I think about what they trace out, they shouldn't leave a disconnected subtour, but these are things you can check in polynomial time. And that's it. This is the entire algorithm. It's a nice, complicated dynamic programming problem. Certainly, it's at the level of solvability for thinking through in CP. The only difference is this is obviously not practical. The running time is n to the O of 1 over epsilon, but this was important enough that it was worked down so that the running time, the dependence on epsilon, does not hide on top of n. In fact, it's nearly linear in n. So that's, I don't know if there's any questions so far, but that's one nice problem that has a good CP flavor once you realize you're just dealing with these portal respecting tours. Okay. Well, now here's the part I was really uncertain about. Do I show how I extend this in recent work? And I think I should, because now I can talk about personal experience with this and how CP inspired me to come up with a much stronger solution, with a strong solution for another problem. Now, what I'm going to describe so far, all we have is poly time. We don't have like that semi-practical version, like on the previous slide with the n log n. We're just at that we got poly time. Maybe we'll work on making it faster later, but we're happy with this right now. So let's go back to CVRP. Remember, the vehicle can only serve C clients at a time before it has to come back to the depot to resupply. Or a different way to think about it, the vehicle can only pick up C scooters and then bring them back to the depot. But this is just a single depot problem. A very recent result that I just submitted it a few weeks ago, is a 1 plus epsilon for this in the Euclidean plane. And I want to talk about how CP helped me bring this from, well, the standard TSP algorithm to the new one. Now, it turns out, and this is the part I'll skip, it suffices to show that multiple path TSP, where everybody starts at S and ends at T, and you have to send precisely a known value M from S to T, and you don't worry about capacities. We have this nice reduction that shows that if you can approximate this uncapacitated multiple path problem, then you can solve CVRP. So now it sounds a lot like TSP, except there's multiple salespeople instead of just one. You can still do the quad tree, you can still put portals, you can still look at the optimum portal respecting solution. None of that has changed so far. If we can find the optimal portal respecting solution, then we get a 1 plus epsilon for the approximation. The problem is now we can't prove that it's sparse at the portals. There could be multiple salespeople that pass through a pair of portals, pass through a portal. So I've annotated this picture with how many salespeople enter through one portal and leave through the other. And I'm not worrying about both ways, the picture gets messy, but let's just say there's 4 salespeople that use this pair of portals, 3 salespeople that use this pair of portals. They might actually visit different points within the square, but they do enter and exit through those portals. So since we can't assume they're constant, we can't use that nice Catalan number bound, because we need to know how many salespeople use a pair of portals. Our DP algorithm still needs to track these. And what I want to talk about is, again, the standard CP problem. My DP is too slow, let's make it faster. So that's exactly what I'm going to do. Nothing special about that, it's just there's some neat details. So we're going to come up with a fast way to do this. If we could somehow write a dynamic programming algorithm that was parameterized by all of these numbers, then it would work just fine. But that is too slow, it's not polynomial. Now, this is what detail. You can forget about this detail quickly. I just want to point out what we leverage. First off, we point out that you can assume that all of the numbers on the edges, so the number of salespeople, is basically a power of 1 plus epsilon. So there's only logarithmically many of them. There's a floor there that's a bit of a nuisance, but it has to be an integer number. We can assume this and lose an epsilon in the approximation guarantee again. So not only are we looking for portal respecting solution, but we want that as well, that all those numbers are powers of 1 plus epsilon. So we're getting close to polytime. For each of the, there's like O of log, like O of log n different pairs, and each of them has one of O of log n different numbers on it. The combinatorics doesn't quite make that polynomial yet, though. So the second thing that we prove is that for portals that are kind of close to each other, sorry, for edges that are kind of close together, the number of salesmen that we use them are comparable. And don't worry about remembering that exact expression, just that nearby edges have comparable numbers. That's all that really matters. So we can prove that there's a near optimum solution that looks like that. And now this fun part, this was my favorite part of this paper. Now we're gonna look at the planar dual of this graph. Right, so it's non-crossing, we still have that property. Oops. It's non-crossing, we still have that property. And so the dual is a planar graph. And since all the vertices of the original planar graph are on the outside, the dual is a tree. We're gonna do something pretty nice with this tree to finish it off. Now, if you're forgetting what we're doing, you may have lost the plot here. The whole point is to show that we only need a polynomial amount of information stored in the DP table. We're trying to show that we can somehow represent all these k values using only polynomially many choices. All right, so 2 special cases. If this dual graph happened to just be a big, long red path, then that's nice for us, because we can just, in the DP table, we can store the exact value for one of them, and then the rest we can just talk about the difference as we trace out. There's a polynomial number of possibilities. Because we have this nice smooth property, which I told you to forget about. But the change from one edge to the next is not very much, and we can index the DP table with that. On the other hand, if the planar dual here was a bounded height tree, where p is the number of portals, the number of nodes there, if it's an O of log p height tree, we have another trick that I won't get into, but we can also show that the number of different k vectors is limited to. Now, if I'm a competitive programmer and I know how to handle a long path and a short tree, what am I going to do to solve the whole problem? I'm sure lots of you know it, and maybe you're just shy. You have a problem, you know how to handle a long path and a short tree. What do you solve it with? What's that? Yeah, exactly. Oh, centroid decomposition. Interesting. That's not quite what I did. I have to think about that one. There's a different thing that I do, at least. But HLD, heavy light decomposition, the heavy path, light path thing. So what we show is that those 2 ideas are compatible, and we can just do an HLD. And with HLD, we have so we use an HLD in the analysis to show that the number of Ks that we have to consider is limited, and also to enumerate them. And that's it. Now we're backing out of the details. So the DP state, it's just the square, the portal pairs without the numbers yet, and then the numbers. Via heavy light decomposition, we show that for any p bar, there's a polynomial number of k bar, and we can enumerate them efficiently. So that's the algorithm. And I just want to point out that due to complications from only considering the structure, these smooth k bars, the combining subproblems and the recurrence is tricky, but we use min-cost flow to do that. So just saying there's another cool thing happening under the hood. The point is we can extend the TSP algorithm to CVRP using ideas that we're very familiar with. Heavy light decomposition, min-cost flow, tricky DP where you can see some dynamic programming algorithm that's too slow, so let's just try to make it faster. And I really should point out my co-authors on this one too. So Fabrizio and Raman are at the Swiss AI Lab. Kenter and Mohammed are at the U of A, just like myself. Okay, now I'm backing out of the details. Other examples. Now, I'm going to talk in generalities again. Other examples of CP topics that actually I've used in papers. I've used Lagrangian relaxation multiple times to design approximation algorithms. This wasn't just some trick that's used to accelerate CP things. It's in this 90s research paper, but there's also 90s papers on approximating things too. And I've used them, well, 2 of those things are papers 2 of those topics are papers I've written about using Lagrangian relaxation. Primal dual, and Richard was just talking about this, this dual potential thing, and it's akin to the primal dual algorithms that I look at, but I use them a lot. I have many papers with primal dual algorithms. One of the bread and butter tools is network flow. It's hiding under the hood for lots of my papers. Greedy strikes really hard with approximation algorithms. It's hard to find a good greedy problem with exact algorithms. They exist, but it's hard, but they're everywhere in approximation algorithms. And possibly 25% of all papers in approx use linear programming. So if you love it, you have a place to work, and if you don't love it, you can avoid it. But it's there. But if you were to get involved in algorithms research, again, I'm speaking through my lens for now, you get to learn a lot more new techniques too that maybe don't have immediate CP applications, but they're just more tools. They feel like more tools, more things you learn about than apply in other problems. And one last thing on this is that you can even generalize the theory of NP completeness. If you like that part of your course, proving things are NP complete, you can also ask about proving things are hard to even approximate. Some problems are very hard to approximate. I was just showing you the good news today, and you can extend that theory. So if you love math and you love your complexity theory, there's a place for you here too. All right, just to wrap up, obviously I spoke about things that I have personal experience with, and I'm overfitting this presentation to my own branch of algorithms research. Algorithms research is a very broad topic with many different ways to look at problems, view problems, prove problems are hard, design faster algorithms. But, I mean, I don't know if this is a useful bullet point list, but I was just trying to think about what are some parallels in general. Well, usually when you solve a problem in algorithms, you're breaking it down into subtasks, like you, not always, but often do in a hard CP problem. It's the same thing, but that's problem solving in life, though. You know, we're building systems and solving them one piece at a time. New problems are often posed, so they just keep popping up. New tech concepts emerge over time. Think about Alien's trick. When that came in, Richard was talking about how a subset of people here really latched onto it and created lots of problems with it. Well, when new techniques come out in research, we do the same thing. The research community buzzes and tries to see what other problems can we solve with this. It's a similar, I mean, there's similarities at least. One thing I love about research is I can work on a diverse set of problems. It's a problem set. Maybe some I'm thinking about messy DP, some I'm thinking about linear programming, but it's not like it's not like my boss told me to work on one task for 2. Intentionally a diverse range of problems just so I don't get overtired by thinking about things one particular way. I guess it's in with most things, but especially in research. Some of these things I mentioned maybe sound a little tough if you don't have much research experience, but a good supervisor will get you started with easy problems that can still be published somewhere as nice little warm-ups, and you'll eventually work your way into solving hard problems. And if you're interested, you could make a career of it. And my favorite part is that getting the email that says your paper has been accepted really feels like an AC verdict. And it feels almost worse when they don't accept it, but the AC feels really good though. All right, so that's it. Just as a closing comment, researchers who have a clue what we do in CP really value this. If you have CP experience, everyone in this room has CP experience, has very, very strong CP experience if you made it to the UCUP finals. Like, a very elite amount of experience. If you're curious about maybe algorithms research as a possibility for your career, or even just maybe post-secondary studies, like graduate studies, even though if you're not settled about what you want to do yet, reach out to any one of us who does research. I talked about algorithms research, but other research is like this too. Just as a quick show of hands, who in this room hires or takes on graduate students for studying with them? Yeah, who takes on grad students? Okay, there's 2 of us in the... okay. And personally, I take on 1 new student every year, so that's always a possibility with me, at least 1 new student every year. And CP experience weighs very heavily. If you look at my students, they don't have a lot of CP experience because people with CP experience tend to go to the big places, but it's certainly something I value highly. And I'd love to catch someone with really strong CP experience at some point. Thank you very much.
Thank you, Zach. Is there any question that you guys want to ask?
how does advances in AI affect research in CB?
Great question. I intentionally left AI out of this because I know we had some other sessions on it. So I'm not as good as some of my colleagues at following this. All I can say is that I've sat down and argued with Gemini Pro, which is what the university pays for, tried to get it to prove little lemistry, and it hasn't yet. Now that might be my lack of creativity in engineering a good prompt, but I have tried for a while. But I know that some of my colleagues have had some problems solved. It's getting really good at some things like these gradient descent style algorithms, like generating novel ideas there. Ask me this in 2 years and I might have a different answer. I actually, just very quickly, 2 days ago, I woke up way too early because I haven't adjusted to the time. I still haven't adjusted to the time. I woke up way too early and asked and decided I want to pursue this counterexample idea I had in my mind for something. So I asked Gemini again, because that's what I have, to referencing these papers that have similar counterexamples, please give me a counterexample to this. And it proudly gave me a counterexample, and I dismissed it time after time after again, showing it why it wasn't. So something was off. It never did produce one for me, even though it confidently said, here's a counterexample. And in a separate case, when I was looking for a counterexample, it confidently presented one with a paper I hadn't seen. I followed the paper, and the paper actually proved what I was looking for, not provided a counterexample. That was like a year and a half ago. I'm sure it wouldn't do that now. Yeah, I don't have a great answer.
Okay, any other question?
Wait, can I ask, like, why do you choose approximation, like, algorithms, and like, how you go into this field?
Okay, so the reason I chose approximation algorithms is because of the supervisor that was at the school I went to. I made a bit of a Canadian choice and chose a grad school that was close to where I grew up. And it turns out the primary theorists there are specialized in approximation algorithms. And since I was a theory-minded student, that's how I got started. So I kind of got defaulted into it, but I'm very happy I did. No inspiring stories there. Yes?
Can you please repeat how the approximation scheme works? Like
Repeat how my scheme works?
in the algorithm for plane.
The vehicle routing scheme. You repeat roughly how it works?
These portals here.
Yeah, so...
Well, why is this approximation scheme is 1 plus epsilon?
Okay, so at a very high level, it's a 1 plus epsilon because the optimal solution that goes through portals is at most 1 plus epsilon times the true optimum. So then we're just going to hunt for the best solution that goes through portals. So that's the main reason that drives it. I lose my epsilon when I restrict my attention to portal respecting. Now, I didn't talk about why it increases by only an epsilon, but if you can imagine this grid, this quad tree, and you randomly shift it around, every edge that happens to get, when it happens to get cut, in expectation, you can prove this, it only has to divert an epsilon factor of its length to go through a portal. So that's the part of the analysis I skipped. When an edge is finally diverted through a portal because it's cut, in expectation, its length increases by epsilon.
So it's also randomized, yeah?
What's that?
It's also randomized.
Also in the math? Oh, sorry, I didn't hear.
Is this algorithm like deterministic or randomized?
Oh, okay, so I gave a randomized approach to it, but you can try a polynomial number of grids, and one of them will be as good as the random grid expectation, yeah.
Okay, if that will be all, then thank you, Zach.
Yes, thank you.
Okay, our last talk today will be by Stanley Wade. So he's a third-year PhD student in Princeton. More importantly, he's a contestant of the team we play mod in the Northeast. So he will share his research about the competitive programming in the AI era, and can large language models solve, author, and optimize.
Okay, thanks, Jingbang, for the introduction. Yeah, so I'm Stanley, and as Jingbang said, I'm a contestant on the team. We play with mud in the Northeast. And so these slides were prepared by me and my teammate, Zere, and also a collaborator on some of these projects. Yeah, so I guess today I'll just be talking about, yeah, like AI and competitive programming and like how we measure it and how can we use AI to improve competitive programming. Yes.
Sorry, I have a very quick question for you because of Zach's talk.
Uh-huh.
Is Sanjeev Arora your advisor?
Yes. Yes. Yeah, that Aurora, yeah, that's my advisor. But he doesn't work on that area anymore. Okay. Yeah, so to outline my talk today, first I'm going to talk about Live Codebench Pro, which is basically evaluating competitive programming. And then second part will be on Frontier CS, which is evaluation of LLMs beyond competitive programming. And then I'll talk about a project called AutoCode, which is does two things. One is using LLMs to generate test cases, and then also using them to generate new problems. And I'll summarize the talk. The lead AI, head of AI at like Tencent AI Labs. Yeah, so he says in a blog post here, what should we be training AI to do and how should we measure progress? Well, benchmarking is, well, training is the first part of this, but also benchmarking and measuring AI performance is the next part, which is important. And I'll start off by talking about this benchmark, Live Codebench Pro, which was presented at NeurIPS 2025. Yeah, so these are some tweets highlighting our work. Yeah. So I guess as a disclaimer, these slides are slightly outdated in terms of like timeline for AI, as in like these statistics and results are as of May 2025, which is a very long time ago in this field. But yeah, like this benchmark, essentially what we're trying to tackle are these three problems. So yeah, like if you look at the benchmarks that these Frontier Labs have released, again, back in May 2025, they have high solve rate, like if you look here, but they run into the issue where it's like unclear how much, like what the distribution of like different categories of problems are, right? And so our evaluation with Live Codebench Pro, we sort of annotate some problems and look into this. Second thing is, yeah, so like what exactly do those statistics mean? Without any detailed breakdown, it's really just unclear. Like, is it really super intelligence or is it just, you know, using some sort of engineering hacks to get average human? Unclear, right? And then third thing we tackle is the problem of data contamination. Yeah, so the main issue with this is that, like, if you look at Frontier Labs, when they evaluate their performance on competitive programming, they update the tasks like every 3 to 6 months. And unfortunately, like right after contests, the editorials and stuff and discussions come out very quickly, right? And nowadays, when AIs are given access to tool usage, it's very plausible that they can just access online tools. And even without access to online tools, it's likely that they might have been like trained further on the new data. So our benchmark, yeah. So to tackle the first problem, like the first two problems, we want to like sort of benchmark the AI on different types of tasks, different difficulties, different categories. So to start off, yeah, as we all know, there's like different difficulties of tasks on Codeforces or whatever, and AI has like different abilities to solve each level, right? And yeah, so again, this is back in May 2025, but if you look at the Gemini model, their best model was 49% on medium problems, only 6% on hard problems, and they had like a grandmaster rating, right? Obviously, it's different nowadays. This was a year ago, but back then, right, it was important to benchmark these competitive programming, right? I mean, even now it still is. A lot of open source models, it's way behind the frontier models. And really, even the frontier model, it's probably just like GPT Pro that's like really able to do, and of course the company's internal models. So in this benchmark, so our team like has a lot of former competitive programming people, and so we did a lot of data annotation, for example, to categorize which problems are knowledge heavy, logic heavy, observation heavy, right? And basically like given these like categorizations, we can design this benchmark to reveal several different diagnostics regarding these models. First is that LLMs, they're better at structured reasoning, like more standard stuff compared to creative insights. Yeah, so that's the first thing we saw. Second thing is we analyzed some failure modes. For example, LLMs, they struggled with more conceptual errors, but they would have less implementation errors. Obviously, if you guys have used LLMs, you would maybe see that the cost of this is that they have super long code, right? Like maybe each block of code represents some standard thing, but they have to, yeah, they implement it. But of course, they have less errors. Yeah, third thing we observed is so the power of like parallel generations at inference time. Like for example, PASSAT-1, it only reaches like top 5% of human, and PASSAT-10, it of course does a lot better. And like even though this statistic is from a year ago, like this is of course still going to be true nowadays, right? Like scaling inference time. Yeah, so fourth observation we have is that like with reasoning and non-reasoning models, there's huge gains on, like reasoning models have huge gains on the knowledge-heavy ones, but still like with the observation-heavy ones, like more ad hoc ones, it still kind of struggles. Yeah, so that's one thing we noticed. Yeah, so that wraps up the part about the benchmark we did, so Live Code Pro. So like, even though this benchmark is from a year ago, like regardless, I think it'll always be true that benchmarking is important. Yeah, like not necessarily in competitive programming, but just in general. Oops, sorry. Okay, so the second work is, so we want to evaluate beyond competitive programming. So this work is called Frontier CS, which will be presented at ICML 2026 this summer. And basically, you can think of it as like the ICPC challenges or UCUP challenges, that sort of contests, right? Those sorts of problems that we're trying to evaluate LLMs on, or at coder heuristic contests, that sort. Yeah, so Frontier CS is essentially going from these closed form short, like very much verifiable CP problems to these open-ended problems where it's unclear what the optimum is. So some sort of generalization is needed to go to these sorts of tasks. If you look at real CS tasks, they're very open-ended, and any sort of optimization that beats the state of the art will likely lead to real value. And of course, now there's no like standard technique because you're trying to beat the state of the art, right? And it's never been done before. So that's real CSS. And to sort of like benchmark LLMs on these tests, we like Frontier CS, you can think of it as like a surrogate by using these hill climbing tasks that can be done. And actually they're like, if you think about these problems, they're like actual real problems that are abstracted out from what people in industry face. And it's easy to measure progress. Yeah, so for the design of this Frontier CS benchmark, there's two types of problems that are in this benchmark. One is more, the competitive programming split, really what we mean is like the heuristic contest style ones. And there's also another part which is the research style tasks, yeah, like operating systems, high performance compute, et cetera. And so the properties of these, like, obviously these are challenging problems, and you can always find a way to beat these by using some deterministic score function. And so like the judge, so you can look at some example problems here, but the judge, it's basically like the way to score this is like if it beats the state of the art, you'll get a lot higher score, so like 100 points, right? And suboptimal solutions, you'll assign it partial score. And so if you look at these benchmark scores, actually the scores will like always be changing depending on what the state of the art is. Yeah, so this is Frontier CS, which benchmarks these more open-ended problems. Okay, so for the next part, we're going to talk about autocode. But to lead up to that, I want to start off with this quote by Rich Sutton. He's like a leader in like RL theory and like basically like a legend in the AI community. So a quote by him, he says, "AI system can create and maintain knowledge only to the extent that it can verify the knowledge itself." So basically, like you want to know how, like, it would be ideal to have AI that can like know if it's, for example, improving, if it's getting stuff right, and that's how it can get like the signal to learn. Oops, sorry. Okay, so yeah, so part one of autocode. So we're trying to design a pipeline. So autocode was presented at iClear 2026 earlier this year. And so the first part of autocode is using LLM, like trying to make LLMs test case generator for these competitive programming problems, right? Like if you think about code forces, all the test cases, they're hidden. And it would be ideal if you could just somehow generate these cases locally, so you don't like, what's the word? Cloudflare the Codeforces website, right? So if you could have these cases generated locally, that would be very desirable. Yeah, so how does this part of autocode work? Well, okay, so I guess this slide was for a non-competitive programming audience initially, so it's like we're talking about how test cases work, which I'm sure you guys are all familiar. But good suite of test cases I want to highlight is they should be robust against cheese solutions. They should also be, of course, logically sound and correct, and they should be efficient to evaluate, right? You don't want to cover like the entire space of test cases, right? Like maybe 100 test cases is good. Yeah, and the first point is especially important because if you want to really ensure that the cases are correct, like if you don't have like good cases, of course, there's going to be reward hacking by humans or LLMs, right? Yeah, so what's the approach to generating test cases? Well, basically, this is a agentic pipeline, so a lot of prompting and like automated prompting, I guess, to reflect human preferences for what like good test cases are. And so, yeah, the agentic pipeline basically has three parts. One is the validator, which like validates whether or not a test case is like reasonable for a given problem. Next part is generator, where you try to generate the hard test cases. And then finally the tester, which does the evaluation of these and provides feedback on like whether these like validator and generator pair is good. Yeah, so it's something like this. And so if you look at the results of this agentic pipeline, which is really just a bunch of prompting with like automating the prompting, right? If you look at the improvement on LLM-generated solutions for these CP tasks, you can see that autocode improves the consistency compared to like more naive test case generation strategies. Consistency meaning like consistent with, say, Codeforces verdicts, right? And for human in-context solutions, it turns out that autocode is way better than like previous works that try to also solve this task of like test case generation. And so some implications of this part of the pipeline is that it's like clearly it's relatively reliable, and so we've already like integrated this into a new version of Live Code Bench Pro, and yeah, so that's good. And of course, like if you have good test cases, you can design a RL environment that that you can use to like for our LLM training on these sort of tasks. Yeah, so part two of autocode is how to use LLM as problem setters. Yeah. So again, it's this agentic prompting pipeline, but we go a step further and like find a way to like improve LLM's problem generating ability. Because if you think about the way like humans improve, right? We sometimes think about more novel problems to like improve our ability to like solve harder and harder tasks. So it's like some self-improvement paradigm, and this is like one concrete step towards that. So essentially, you have the validator, generator, tester, but now to like actually figure out if a task is good, you have to do some, I guess, augmentation, right? And this could come from like maybe stress testing, like brute force and reference. And so, yeah, if you basically like upon running this pipeline, turns out that like if you look at the self-improvement loop, it's like you get increasingly better, like increasingly higher quality problems that this LLM pipeline can generate. And so these are evaluated by some like a team of competitive programming former contestants, I guess. And yeah, so this is the takeaway. Like self-improvement is a huge area of work nowadays, and this is like one step towards it. And yeah, to summarize, so the first part is LLM test generation. Essentially, yeah, you can get like a pretty good judge locally, and of course, like using this local judge, you could very feasibly design a RL environment to use. And for task generation, to summarize, self-improvement, that's the main paradigm here. And yeah, so cheap training data, like essentially you're, like if you're just running this pipeline, it's not gonna take much compute, right? Yeah, and of course, generating new problems for humans, it's always nice to have, right? Like higher quality contests. Yeah, so to summarize the 3 projects that I've just discussed, yeah, Live Code Bench Pro, AutoCode, and Frontier CS. Basically, like the goal ultimately is to not just stay at competitive programming, but to like go beyond these and to like actually solve novel research tasks, right? And like push science further. And so this is just a summary of yeah, how these 3 works link together. Okay, and finally, I want to conclude this talk with some thoughts about AI and Universal Cup. So our team, we play with Mud in the Northeast. We actually made very substantial use of AI during the semifinals. And actually, we were very shocked at how good AI was. I mean, it allowed us to qualify for this finals. And I guess it wasn't against the rules at the time, so we use it. And I guess we probably had the most success in using it. So the disclaimer here is like we still did the on-site finals yesterday officially without AI assistance beyond the allowed prompts on the UCup website. So yeah, I really want to thank Jingbang for allowing us to still compete for this. And actually, like we communicated the semifinal situation with him right after the contest, and the committee they were able to add like a final slot to not affect like the normal advancement of non-AI users, I guess. Yeah. So with that being said, like given that we did qualify with AI, our goal coming in was, can we do better than last place? And so here's the frozen scoreboard before the freeze. Yeah, before the freeze, we were at last place. I'll let you guys find out later if we reached our goal. Yeah. So yeah, that's that. And I guess some concluding thoughts on AI and competitive programming. So I guess AI cheaters are annoying, but I hope they shouldn't make competitive programming less fun than it is. We're all here to like enjoy human challenges, right? And if you think about it, LMs, they'll never be able to like truly enjoy it in the sense of like getting a dopamine hit from like getting ACs, right? Well, until like AI is conscious, but I mean, for now, that's not the case. I guess like going forward, probably for more important contests, increased proctoring is probably needed, unfortunately. And I think, for example, UCup is doing a good job of this. At Coder Grand Contest, they're also doing this. It's a good start. I guess one more thing I'd like to add, I didn't put on the slides, but I think possibly a future, like because AI is a huge thing nowadays, possibly like these hybrid AI and human contests could become a huge thing soon. Like Midnight Code Cup is something, and I actually think that would probably be a cool addition to like this competitive programming field in the future, because like really, like if you think about what people are doing in industry nowadays, they're doing a lot of like agentic coding, and like agentic coding like ability is going to be very important as well. And so I think going forward, that Midnight Code Cup or contests of that flavor would be very cool to keep doing. And I guess going back to traditional CP, like human competitive programming, I still think it will continue to be useful, but now in a different sense. So in the past, I would say like, I think we would all agree that competitive programming is useful in improving like our problem-solving ability, implementation ability, math thinking ability, right? But I think in the future, it'll be important, but for slightly different reasons. Like the first one, of course, problem-solving will still remain true. The second is being able to understand new domains at like both a micro and macro scale. So like rather than like execution, like understanding of like large domains of knowledge it will continue to be important. And third is just ideation ability, I guess. Like as a PhD student right now, what I've noticed is that these LMs, they're still pretty bad at like giving ideas, but they're pretty good at executing like instructions that you ask, like given that you have a good idea. And so like ideation ability is something that we sort of develop as competitive programmers, like when we think about like how to, I don't know, cheese new algorithms or massage algorithms to work for a time limit, right? This will continue being important. And I guess one could imagine a future where thinking it could be like delegated to these models, like implementation of ideas, execution of like brainstorming stuff. But nevertheless, I would say in such a world, like being able to understand like large domains of knowledge, whether it's competitive programming, pure math, robotics, or even AI itself, like it's gonna be like arguably more important than now, right? Like the ability of humans to understand and verify things, right? And to conclude, to be good at this stuff, we need to be even better at thinking and problem solving, which is exactly what human competitive programming trains you for, right? Yeah. And so with that being said, that's all I have for today. Yeah, thank you so much.
Okay, thank you, Stanley. Any question? Anton. Oh.
Could you give an example of a novel problem created by AI suitable for IOI or ICPC, and have you actually used any in real contests?
Okay, so that I don't really have access to the data for it, but like it's in the like paper. Yeah, if you go into that, yeah, yeah.
At some beginning, I guess, you talked about the classification of the problems, I guess, idea-wise or whatever, and and they were very, I don't know how to say, fine-grained, as in some ideas, for example, game theory or like idea task and like whatever. What is the justification for it, and who came up with it?
Oh yeah. So that's like, yeah, good question. That's like part of our goal was to like really see like how LLMs do in like more like given a fine-grained classification of different tasks, how LLMs do. And so like our team was a bunch of like competitive programmers, and so we did discussions of like what's the best way to like make this hierarchy of like classification of problems, and we ended up with roughly something like that, and we just did data labeling on, yeah. What? Sorry?
What's the end of the discussion? Like, I mean, I'm asking for reasons why you're able to come up with such kind of classification, which I think I mostly disagree, actually.
Oh, okay, maybe let me go back to that. You're saying like, are you saying this? So this is so what would you suggest for a different classification?
I'm not suggesting that there is a different classification that can match this. I'm saying the topic as is cannot be just blindly fall into that category. I can see that why you're reaching to that conclusion, but I think this is quite wrong actually. I think this is quite wrong. I think some of them, for example, greedy. Game theory. I would just put it at knowledge abbey. I think
game theory.
Yeah.
Yeah, like so some I guess some problems they could fall into multiple categories, and yeah, it's not necessarily like mutually exclusive, right? Like, would you say there's another category that we missed?
I'll rather say that categorizing whether the problems are knowledge heavy, logic heavy, or observation heavy should not be based on the topic the way that the solutions are constructed. Yeah.
The way the solutions.
Yeah.
Okay.
The way that the problems are designed and the solutions are constructed.
That's true. Yeah. That.
For example, you can have knowledge-heavy combinatorics, logic-heavy ones, and
Mm-hmm.
so maybe it cannot be broken down just by the topics.
Mm-hmm. Yeah, that's true. So I guess we did like try to think about like how the solutions were like when annotating as well. Yeah, because like some you can imagine there might be something very standard in some like some category, but it's like in some like really hard category, right? Something like that. Yeah.
Prompted to solve it all?
Okay, good question. So yeah, I didn't write it in the slides, but essentially, like during the contest, we started off with I guess using GPT-5 thinking, and we got some stuff, but it felt kind of bad. And then we tried using Pro, and that was like scarily good. But for some reason, like if you go on the semifinal scoreboard, there was a really easy problem that it just really struggled for a very long time, and we had to fix that by hand. Yeah, and then for some other problems like the geometry problem, like we had the geometry problem, but it wasn't able to one-shot it. We had to like, for example, tell it to stress test, like prompt it to stress test to fix it, and then it passed. Yeah, but back then we didn't really use a agentic pipeline. Besides, like we just used chat prompting. But really, like what's behind the scenes for like GPT Pro is definitely some agentic pipeline, some orchestration that they're doing. Yeah. Okay, let's start with him.
Wait, I kind of like two questions. So like the first question is like, is it really realistic to compare like the ELO of models to human ELOs? Like maybe for like early data sets like MNIST, like getting the human accuracy was good because like if the human doesn't get 100%, like the accuracy is like, I mean the data set was kind of bad. But in here there's like no apples to apples comparison between like models and humans, right?
Yeah, I agree.
So like what good is it to like say like the AI is like the top like 1% of humans, or like recently like when models have like published code for the score, the people are saying like, oh, the model is like 7th among humans, which is like really weird to me. Why people still do this? Like, and then the other question I have is like towards the end of the slides, you said like that we should have like programming contests with like AI.
Mm-hmm.
Wait, like sorry Lydia, like I really appreciate Midnight. Oh, I think she's not listening, but like I really appreciate like Midnight Code Cup, and like I really enjoyed it last year. But like this year during the during the qualifiers, there was like a team, I think they got 6th place, which is by pasting the statements into like ChatGPT and like pasting the output back into like the prompt statements. And I think like the rate of AI progressing right now is like so fast that like maybe for next year, like if Midnight Code Cup still like allows AI use, like it'll just be like who can pay Claude the most money.
Mm-hmm. Okay, that's true. Good question. So for the first question, you were saying, yeah, I agree. It's probably not a apples to apples comparison. You can think of like models; they have like infinite implementation speed in some sense, right? So really, it's like I think probably. Yeah, I think for AI, you should not really compare it against humans, but we should acknowledge that like these AI, they are indeed like pretty good at solving like really hard 3000 level problems, right? Yeah, and for your second question, yeah, Midnight Code Cup. So, okay, that's a good point. So maybe half a year ago, I would have proposed like a future possible contest style to be like humans plus chat prompting for these normal algorithms contests. But very quickly I realized like these AIs getting like really good at it. So like I think that would just be like AI would just like AK it and it would be like there would be no point. And so yeah, that's why today I propose maybe like agentic hill climbing, that sort of thing is a interesting new contest direction. But I guess your point is saying like possibly AI could all get really good at that.
Wait, like Midnight Code Cup is optimization contest.
Yeah, yeah.
And AI got like. Wait, like is it not? It's like. No, wait. No, wait. I mean, like the qualification was like optimization contest. I was just like. No. I was just like giving the example of like qualification round. I'm just saying like. No. Okay. But like I was giving like. I was like giving concrete example of like, qualification because I like personally know the number 6. So like I'm just giving example of qualification for Midnight Code Cup because like I personally know the number 6 team. They're like another Singaporean team, and I just asked them like what they did because how did they get number 6? They used the free ChatGPT, just paste the statement and paste the output back, and like apparently that got number 6.
Wow.
Yeah. So I was just I mean like I'm not like I mean like I appreciate like Midnight Code Cup like last year, but like I like wonder about like the contest format for like future years, especially like 1 year later, you know. Yeah.
Yeah.
I wonder if like Lydia wants to like speak on this also. Okay.
Like one possible solution could be like give everyone access to the same like API model, like Claude Code 4.6 or something. But yeah, it's unclear, right, in general.
I mean, like people in chess, there used to be contests in chess where like people used to like have augmented with like chess like models, like chess engines or whatever.
Mm-hmm.
But I mean nowadays like like no one does that anymore. Right? Like it doesn't really make sense, right?
Yeah. Interesting question for the future though. Oh, we have one more question over there.
Yeah. I see the. It's very far away.
Thank you for the presentation. And my question is, how much of the self-improvement in your slides are you believe is true, and how much of them are you consider it's bragging or something like that? Because you said that the LLM can propose a task that can be solved by the LLM, but from my experience, I believe many of the like extension to the problem are trash, so there are no meaning at all, and I don't think they can be helpful to like improve your AI. Like I mean, basically, I believe that if you present a code and you ask the LLM to hack the code, which we did, one thing I can share is that we did that during preparing the contest. But now, I don't think there's something like self-improvement to be meaningful at this point. Mm-hmm. And what is your thought?
Yeah, so I don't know the specific details of like this one, but like I think in general self-improvement should be like taking off pretty soon. Like you can imagine a language model, a language model could get a better version of itself simply from like orchestrating it during inference time, like making like a agentic version of itself. And then the model gets access to like this stronger version of itself, and then it's interesting like future work, but I can imagine this sort of pipeline could like continuously improve the model itself.
Okay, thank you.
Right. Yeah.
Okay, any other question? Okay, and then thank you, Stanley. I guess that will be all. And we also conclude the conference section, and I hope everybody enjoyed this morning about these 3 different topics, but it seems to be AI and CP related. Okay, that will be all. And I will give time to our volunteer, so we should move to lunch, right? Yeah.
应该就是午饭时间吧，下一个。对。